class, I will explain about best response curve. Best response curve is considered 2% games in your best response with the maximized payoff. The table 1 shows the row and column payoff. The second table shows the column choices and the row response. And you can read it like this. If column choose left and row choose top, and the payoff will be 2.1. But if the row choose top and the column choose right, it will be 0.0. In this case, you must find the best payoff. So, in the second slide, you see the formula from the table 1 and 2 that I discussed. Like that. And the third slide is about mixed strategies. Mixed strategies is finding the equilibria of mixed strategies and pure strategies equilibria. You can see the first slide, same like the first table. Same like the first table in the first slide, and the second table from the side. You can see the probability of the choices you made, and this is the formula and what the sign means in the bottom of the slide. So from the probability table, you can see the formula in the slide 4. This is the row payoff formula, and if the R becoming the delta R, this means there is the change in R. The formula changes to this one. Then this is the column payoff formula. Then if C changes to delta C, becoming this formula. And the last one I will discuss about game coordination. Game coordination is about payoff to the player and highest because they're coordinate. Basically, if you want the best payoff, you must coordinate with others. There is 4 game coordination: battle success, prisoner dilemma, assurance game, and chicken. The first one, battle success. This game is about 2 boys and girls want to meet up in the cinema, but they don't have the cell phones, and they don't have the booking, so they don't know what movie they want to come together. The boys want action and the girls want art. The possibilities that these 2 children came to the same, these 2 children's meet up is the equilibrium is first they together was art, or together was action, or they both go separately. So to solve this problem, you must find another solution, like seeing the location of the art and the action movie, where is the nearest from the house of the both, so they can see where is the possible payoff that is very best from death for both of them. The second thing is prisoner dilemma. Prisoner dilemma is about 2 prisoners, and if they're in jail, if they're implicating other or deny committing crime, confessing is a dominant strategy. Even though coordination is far more superior than term of payoff, coordination will make the prisoner choose their payoff. The one way this approach is enlarge the game, adding choices like contract, saying that they will stick with the cooperative strategy. He or she may find or be punished in some way. So this is about the prisoner giving the contract, so they can find the best way out of the problem. The second one is assurance games. The assurance games is about US and USSR, the Russian. So the choices is to make missiles, nuclear missiles, or refrain it, or doesn't make it at all. This problem is if they do make the missiles, they have the assurance. They know that they will be safe. But if the other make missiles and the other don't make missiles, this will be a problem. So the other one cannot be safe. So if we in the world want the US and USSR don't make missiles at all. To solve the problem, we must either of one check say to the other country that they don't have missile. How to do that? They have opened up the country and say to please inspect it because we don't make it. They should have the assurance to the Russian or the US that they don't make the missiles. So both of them will not make the missiles. The last one is about chicken. Chicken is two teenagers want to have a car in the road and want to crash into another. The first one to bail out to go to the right or to the left will be the chicken. So to solve this problem, the one of the first car must have a lock on the car and tell that they lock the wheels on the car, then they will not go left or the right. So the second one will know that that he must or she must bail out because the first car will not bail out because the crash is not an option. If it crashes, it will be terrible. Okay, thank you for the time and see ya.
Hi, my name is Vio and I'm going to explain about the games of competition. This is a zero-sum game, so called because of the payoff to one player is equal to the losses of the other. So it basically means that when one player wins, the other loses, so the payoff sums to zero. Most of the sports are zero-sum games. In this particular PowerPoint, we're gonna illustrate that the zero-sum game by looking at soccer or football.
So the row is kicking a penalty shot and the column is the defending. Row can kick to the left or kick to the right. Column can favor one side and defend to the left or defend to the right in order to deflect the kick. So let us assume that the row will score 80% of the time if he kicks to the left, and column jumps to the right, but only 50%. If row kicks to the right, we will assume that he succeeds 90% of the time if column jumps to the left, but 20% of the time if column jumps to the right. If row kicks left with probability, he will get an expected payoff when column jumps left and when a column jumps right. Row wants to make this expected payoff as big as possible, and column wants to make it as small as possible. If column believes that row will kick the row will kick to the left half of the time, then the column will want to jump to the right, since this is the choice that minimizes row's expected payoff. So this is the row's strategy. These two curves shows that row's expected payoff as a function of P. The probability that he kicks to the left, whether P he chooses, column will try to minimize row's payoff. So if row kicks to the left 70% of the time and the column responds optimally, row will have an expected payoff of 50 times 0.7 plus 90 times 0.3. 0.3 is from 1 minus 0.7 is this part. It equals to 62. Okay, next. So this is the column strategy. From the column viewpoint, it is maximum of the two lines that is relevant, since this reflects row's optimal choice for each choice of Q. The diagram depicts their lines in color. Just as before, we can find the best Q for a column, the point where row's maximum payoff is minimized. So this occur where 50Q plus 80, it shows in this line, and then equals to 90Q plus 20 times 1 minus Q, which implies to Q equals to 0.6, this part. So if column jumps to the left with probability of 0.6, then row is indifferent between kicking left and kicking right. And then if column responds non-optimally, we can use best response curve. We have already seen that when p is less than 0.7, column will want to jump left, right? And when p is greater or bigger than 0.7, column will want to jump to the right. So here, p is less than 0.7, column will want to jump to the left. And if p is greater or bigger than 0.7, it will want to jump to the right side. So this is where they intersect, in the point where the p is in 0.7 and then the q is in 0.6. This is where they intersect.
So next is games of coexistence. The most famous games of animal interaction is the hawk and dove game. This game is involving a single species and that exhibits two kinds of behavior. For example, here, if two wild dogs come across a piece of food, they have to decide whether to fight it or share the food. So the fighting is the hawkish strategy, which is one will win and one will lose. And the sharing one is called dovish strategy, because hawk is aggressive and dove is more kind, yeah. So as we can see in the table here, if both wild dogs play dove, for example, if both wild dogs play dove, they will end up with this 2.2. And if one plays hawk and the other plays dove, hawk, dove, or hawk, dove, the hawkish player will win everything. They will win everything, yeah? But if both play hawk, each dog will be seriously injured. As you can see here, -2. It obviously can be an equilibrium if everyone plays hawk, right? Because if some dog played dove, it would end up with, if some dog played dove, it would end up with 0 rather than -2. And if all dogs play dove, it would pay someone to deviate and play hawk. So there will have to be some mixture of hawk types and dove types if you want to reach an equilibrium. Suppose that the fraction playing hawk is, we call it P, right? And then the expected payoff to the hawk type will be, this is the formula, H equal -2P plus 4 times 1 minus P. And then the expected payoff to the dove type will be D equal to 1 minus P. So if hawk is greater than D, we would see the fraction of the hawk types in the population will increase. And if the hawk is less than dove, we would expect to see the number of dove types increase. The only way the population can be in equilibrium is if the payoffs to each type are the same, which this requires h equal minus 2p plus 4 1 minus p equal 2 times 1 minus p equal d, which solves for this. So this equilibrium is sort of stable because when p is greater than a half, there are many hawks. It is better to play dove. On the other hand, when p is less than a half, there are many doves. It is better to play hawk. This is called the evolutionary stable strategy, or ESS. ESS was designed to model animal behavior under evolutionary forces. So this is the graph for the hawk and dove game. As you can see, the payoff to dove here is in black line. This is the fraction playing hawk. This is the payoff. So when p is greater than a half, the payoff to hawk is less than dove, and vice versa, showing that the equilibrium is stable.
Today I'm going to explain about the game of commitment. Game of commitment, commitment efficiency, self-enforcing agreement games. We consider it is a two-stage games, which is called game of commitment. And now I'm going to explain about the frog and scorpion. A common interpretation is that people with visions, personalities, cannot resist hurting others, even when it is not in their interests. And the last topic is about the bargaining. So I'm going to explain the game of bargaining. One in which two or more players bargain over how to divide the gains from trade.